So for my project, I chose to analyze a steel beam as part of a shelter structure. This can be seen here. Moment of inertia can be seen. So the uniform load from A to B. Reaction forces calculated here. Sections and coordinates. From this, we derived our equations for shear force and bending moment. This can be seen here. And then from this, we were able to create the diagrams where the maximum shear stress, 25.63, the maximum moment, negative 13.33 kilonewton per meter, both decrease from A to B to 0. So we integrate the moment function to get the slope equation, which is then integrated again. We get the shear. And this is for the first section, this is for the second section. Then we analyze boundary conditions, so fixed support x1 equals 0, therefore theta equals 0, and so forth. We use this information to solve for the constants. Then we can get these final equations for slope and deflection. Yeah, this is deflection. As can be seen, it's this cantilever structure, so they both occur at the same free end, the slope and the max deflection, just calculated here at 2 meters from the fixed end. Okay, so for part 3, involves stress calculations. First step, we found the max bending stress using this formula. This cross section here. They occur at the fixed end, maximum bending stress as well as the max shear stress. As can be seen here, is the bending stress, compressive on the top fibers and tensile, the bottom fibers, increasing as you get closer to the top bit and the bottom bit. Max shear stress, moment of inertia, some of the required distances needed for the equation. This can be seen here in the result. We have maximum shear stress at the neutral axis. It's a parabolic stress distribution, so it decreases as we get to the top bits and bottom bits. So we analyze our beam, we see that we have three points, F1, F2, F3, corresponding to the maximum bending force and shear. So you can see there, so F1, maximum shear, F3, maximum bending, and then F2, we have bending and shear. This is calculating F2. And then, once we have this information, we can go ahead and get the principal stress and max in-plane stress for each of these 3 elements. These calculations here. Once this was completed, we have principal stress and allowable. These were compared to give this ratio, and then the shear and the allowable shear was compared as well in this section. The steel was estimated as being 5 to the 10 to the power of kPa for allowable stress. This value, F3, 444.33 kPa, was found to have the most impact. So from this, we're able to calculate the failure plane, which was 0 degrees. So the direction of the tensile stress parallel with the horizontal axis. So the failure plane is perpendicular, and it's 444.33 kPa at this section, which is most likely to be failure. Yeah.